Hey guys, this is Professor Janacek, and I want to talk about a numerical approximation method used to solve differential equations. Now, numerical approximations are often used if I can't find an exact solution. Maybe I can find something that's close to my solution. This method that we're going to talk about today is called Euler's method. It's a very popular method, also sometimes referred to as the tangent line method, and I'm sure you can guess why, because yes, we will be looking at a tangent line. So let's get started. The first thing we'll do is we'll take a first order initial value problem. So we've got dy dt is equal to some function in terms of t and y, and we have our initial conditions. T of y naught is equal to y naught. Sorry, y of t naught is equal to y naught. There we go, first order initial value problem. It turns out that at that point, t naught, y naught, the slope of the tangent line is actually the function evaluated at t naught, y naught, because remember our function is that derivative which represents the slope of the tangent line. Thus, we can write the equation of the line that's tangent to the solution curve as y equal to y naught plus f of t naught y naught times t minus t naught. Now, this comes from this right here comes from the point slope equation of a line, where my point is t naught y naught and my slope is f of t naught y naught. Now, if t1 is close to t naught, then the approximation at t equal to t1 is equal to, now notice this is giving me an approximation for t1, and what we get, all I'm going to do is take this equation right here and evaluate t at t1. So it'll look very similar. So t1 is equal to y naught plus f of t naught y naught times t1 minus t naught. So there's my approximation for y1. So what just happened when we did all that? So looking over at this little graph I have here, suppose in this situation that I do know what the solution is, and so my solution is this green line. Now, but suppose someone else knows that, but I don't know this. I don't know what that green line looks like. That's what I'm trying to approximate. So I do have, without a doubt, this t naught y naught value. I also have the slope of the tangent line at that value. So that's my differential equation that was given. So because I have the slope and a point, I can come up with this equation, my tangent line here. Now, as long as t1 is close to t naught, I can come up with an approximation. So simply take my t1 value and put it into the equation for my tangent line, and that will give me this solution there. That's my approximation for the y value. So I have a t value, I've just approximated the y value, and you can see that it is a little off from my actual t value, but hopefully if my t1 is close enough, it won't be too far away. So as long as t1 and t naught are really close to each other, this approximation can actually be pretty good. All right, so at this point, the best approximation we have for our equation is this t1 using this t1 value. So now let's use this t1 and y1 to see if we can get another approximation, and that's exactly what we do. So now we have a new equation, my y value is equal to y1 plus f of t1 y1 times t minus t1. So now I'm basically saying, all right, let's take a look at what happens here. Let's get the slope of the tangent line at my next approximation and go from there. Rather than using the approximation, the tangent line that I had before, I'm now going to build another tangent line off of my latest t value. This will hopefully get it a little more accurate as we move further away. So if, again, T2 is close to T1, then I can get an approximate value for T2 at T equal to T2. And what does that look like? Well, that looks like T1 plus f of T1 y1 times T2 minus T1. So you'll notice all I did is I took this equation here and I'm now looking at a y2 value, and I replaced t with T2 into that equation. So this equation here was my best approximation, so that's what I'm going to use for the next step. And then I could continue on. So I would then create a new value, new equation, a new approximation using y2. So notice every time the y values are my approximate values. So I've got an approximation here. I would write another approximation using y2 and continuing on. So you can see similarly I can develop a y3, which is y2 times f of T2 y2 times y3 minus T2. And after that I can build a y4, which is y3 plus f of T3 y3 times T4 minus T3, and continue on. So in general, y sub n plus 1 is equal to y sub n plus f of t sub n y sub n times t minus t sub n. Actually, I'm sorry, wait, back up. I'm actually getting an approximation for y sub n plus 1, so that would be t sub n plus 1 minus t sub n. There we go, much better. There's my approximation at t sub n plus 1. Now, this gets even better. What if the steps are uniform in size? We'll call those h. So when I mean steps, I'm talking about the distance between T0 and T1, or between T1 and T2, so on and so forth. What if I say, let's keep those uniform? Then it turns out that the distance between any two t values, any two consecutive t values, between t sub n plus 1 and t sub n, that distance is h. Which means I can rewrite this even easier. So this distance here will simply be h. And so we would end up with y sub n plus 1 is equal to y sub n plus, instead of f of t sub n, y sub n, I'm just going to call that f sub n. And then again, remember that t sub n plus 1 minus t sub n, that is h. So I end up with h times f sub n. So this would be how I would determine any of those solutions using Euler's method. Now, to find a solution at another point, I could either start over if I wanted some different point, which is extremely cumbersome, or I simply use a piecewise function. And so piecewise linear function to construct this collection of tangent line segments. So I would have my starting point, find a tangent line off of that to get a point. From there, evaluate my differential equation again. Remember that differential equation is given, that's my slope. So figure out what's the slope of the tangent line there, get another approximation, start again another approximation here. So basically continue using that tangent line slope to find my next value, as long as those values are close, and then I would create a smooth curve out of that to get my final solution. And there you have it, Euler's method for numerical approximations. Enjoy!